Imagine looking up at the night sky and knowing that overhead, in orbit, thousands of satellites hum along invisible highways. They carry GNSS signals, relay telemetry and commands, and tie together the world through telemetry, tracking, and command links. They feed ISR feeds to militaries, stream news to your phone, and keep financial networks synchronized. But those same satellites are not just tools anymore, they are targets. Today we'll walk through exactly how satellites can be attacked, the real incidents that have already happened, and the stranger, almost science fiction ideas that experts have floated, because every one of them matters. First, the main methods of attack. At the simplest level, there is electronic warfare, EW. EW comes in many flavors, but the ones to watch are jamming and spoofing. Jamming is the brute force of radio frequency, strong RF signals that swamp legitimate uplink and downlink channels, effectively silencing TTNC and user links. Spoofing is more deceitful. Fake GNSS or GPS signals feed wrong location or timing data to receivers, causing ships, drones, or weapons to steer themselves off course. You can also use selective denial of service on specific frequency bands or more subtle deception to degrade trust in the signals rather than destroy hardware. Next are cyber attacks. Satellites hook into ground infrastructure. Their brains are often on Earth. Breach a ground station or compromise TTNC links and you can inject malicious commands, corrupt firmware, or erase telemetry. Once malware gets into a satellite's onboard software, an operator can effectively lose control of the asset. That is why securing TTNC and ground networks is as crucial as hardening the satellite itself. Then there are kinetic attacks, the dramatic physical option. ASATs, or anti-satellite weapons, come in two main types. Direct-ascent ASATs, missiles fired from the ground that collide with a satellite, and co-orbital interceptors, spacecraft that maneuver into the same orbital plane to cause a collision or force an adversary to drift. Kinetic kills create fragments, space debris, and that debris threatens everything else in orbit. A stealthier destructive class is directed energy. High-power lasers or high-power microwave, HPM systems that can dazzle optical sensors, blind cameras, or induce damage in electronics without leaving a cloud of debris. Directed energy can be used as a temporary denial tool or to permanently degrade sensitive payloads. Finally, there is proximity and capture, approaches that rely on getting close. Satellites that perform rendezvous and proximity operations sometimes carry robotic arms, nets, or grappling devices for servicing or debris removal. In theory, those same tools can be used to capture, immobilize, or disable another satellite. The dual-use nature of servicing technology is a silent and pervasive risk. These are not hypothetical. There are stark, real-world examples. In 2007, China conducted a direct-ASAT test against the weather satellite Fengyun 1C, producing over 3,000 trackable fragments and triggering global concern about long-term collision risk. In November 2021, Russia destroyed Cosmos 1408 in a test widely attributed to its Noodle program. That event generated thousands of new debris pieces and even forced precautions aboard the International Space Station. On February 24, 2022, a cyber attack, a wiper malware incident against KASat/Viasat, knocked out tens of thousands of user terminals, clearly demonstrating how ground network compromises can cripple satellite services during a conflict. Documented episodes of GNSS spoofing and jamming in hotspots like the Black Sea, Crimea, and Syria have misled ships and UAVs. And reports of laser dazzling against optical sensors and ground stations show that directed energy is already in operational or demonstration use. Taken together, these events prove that attacks can be silent and reversible, loud and permanent, or somewhere in between, and their environmental consequences can last for decades. Beyond the obvious methods lie the more unusual, and often dual-use, ideas that blur the line between debris removal and weaponization. Debris mitigation projects such as Remove Debris have tested nets and harpoons to catch defunct spacecraft. Technically real and effective, the same nets or harpoons could hypothetically be used to capture or immobilize an adversary's satellite. Then there's the dramatic concept called Rods from God or Project Thor, tungsten kinetic projectiles deorbited to strike ground targets. That's been a staple of speculative military thinking. Devastating in effect, but outrageously expensive and politically explosive. Commercial servicing platforms, examples include Northrop Grumman's MEV vehicles and DARPA's RSGS experiments, are designed to extend life, inspect, and reposition satellites. Those very robotic arms and tugging capabilities, however, are dual-use. Reprogrammed or weaponized, they could grab, cap, or alter the orbits of rival assets. Other speculative proposals include releasing electrostatic or charged dust clouds to coat and degrade solar arrays, a concept that appears mainly in R&D literature because of its complexity and unpredictability. And finally, a grim historical reminder. EMP effects from high-altitude nuclear detonations, demonstrated in tests like Starfish Prime in 1962, show that nuclear options can damage satellites across wide regions, though such measures would be globally catastrophic and politically untenable. The pattern is clear. Many of the strangest ideas come from the same technical neighborhoods as debris removal and on-orbit servicing. That overlap is what makes modern space technology so fraught. Dual-use capability means that tools created to preserve access to space can be repurposed to deny it. And every time a satellite is struck or disabled, whether by EW cyber intrusion and a SAT, HPM, or a captured grapple, we risk adding to the debris catalog and nudging the environment closer to Kessler syndrome, a runaway cascade of collisions that could make large regions of orbit unusable for decades. Satellites are vulnerable, the threats are varied, and some attacks leave scars that last generations. As we design the next generation of TT&C protocols, build resilient constellations in LEO and GEO, and push forward with SSA capabilities to track everything aloft, we must also reckon with the reality that technical innovation without norms and safeguards can quickly become a weapon. Dual use is not a theoretical worry. It is the central operational risk of the space age. Imagine for a moment the same orbital highways we talked about before, LEO, MEO, GEO, but now from the defender's point of view. If satellites are targets, defense is the art of making those targets harder to hit, less useful to attackers, and, when possible, self-healing. That work spans hardware, software, tactics, and whole new classes of space systems. Let's walk through the concrete measures that keep satellites alive. Start with the hardware hardening. Military satellites are built with rad-hard components, shielding, and error-correcting designs to withstand ionizing radiation, EMP-like effects, and even high-power microwave bursts. Hardening is expensive and heavy, which is why there's a fundamental trade-off between milsats and the cheap, mass-produced smallsats flooding LEO. You can make a satellite nearly impervious, but you pay with mass, cost, and launch complexity. Next is the software and network layer. Encryption, authentication, and cyber hygiene. Protecting TT&C is mission-critical. That means signed firmware updates, robust authentication for commands, zero-trust architectures for ground stations, and strict supply chain security so adversaries can't load compromised hardware before launch. The KSAT/Viasat incident showed how ground network weaknesses can cascade into satellite outages. Lessons learned there are driving major overhauls in how operators secure ground segments. Because space is kinetic and messy, maneuverability matters. Modern satellites increasingly carry small propulsion systems and maintain propellant margins, so they can perform collision avoidance burns or short-term evasive maneuvers against kinetic or co-orbital threats. But fuel is finite. Every evasive burn shortens operational life. That's why maneuvering is a precious defensive resource, used to dodge debris, avert conjunctions, or make an SAT intercept more difficult. Resilience also comes from architecture, redundancy, and graceful degradation. Inter-satellite links, ISL, multipath routing across constellations, and backup payloads mean a single node's loss doesn't collapse the service. Mega-constellations exemplify this approach. With thousands of nodes, the network can route around failures. Scientific studies show that distributed constellations degrade service rather than fall off a cliff when attacked. But they also raise complexity for traffic management and SSA. Then there's stealth and signature management, lowering observability so you're a harder target. That involves reducing radar, infrared, and optical signatures, using narrow-beam communications instead of wide broadcast patterns, employing frequency-agile waveforms and adaptive antennas. These techniques shrink the attack surface by making a satellite harder to detect or jam in the first place. All of this is supported by sensors and prediction. Space Situational Awareness, SSA. Good SSA means dense cataloging of objects, precise conjunction analysis, and better attribution of hostile acts. That's why states are investing in ground radars, optical trackers, and even space-based sensors, the so-called space fence programs, to build a high-fidelity, near-real-time picture of who and what is flying where. Without SSA, defensive moves are guesses. With SSA, they're informed and timely. When active interference happens, satellites employ soft-kill countermeasures, anti-jam transponders, nulling antennas, spread-spectrum communications, and cognitive RF systems that automatically switch frequencies, beam patterns, or modulations to avoid or defeat jamming. Those electronic countermeasure techniques are the equivalent of evasive driving in radio frequency space. Dynamic, adaptive, and increasingly automated. Now consider active defenses, systems that do more than hide or resist. They act. One category is on-orbit servicers as defenders or inspectors. Vehicles like Northrop Grumman's MEV or experimental DARPA RSGS servicers were designed to inspect, refuel, and reposition satellites. In a defensive role, they could repair a damaged satellite, remove a hazardous piece of debris, or reposition a critically important payload. The dual-use problem is obvious. The same robotic arms and tugs that save a satellite can also be repurposed to grapple or disable an adversary's asset. A more controversial option is defensive interceptors or space-based interceptors, SBI. Interceptor craft placed to intercept or defeat incoming assets. Conceptually, they act like missile defense for orbit, but politically they're fraught, technically costly, and escalatory. Several governments have studied the idea, but fielding an on-orbit interceptor fleet raises legal, strategic, and cost questions that make them a last resort discussion rather than a current staple. Another on-orbit option is electronic countermeasures in space. Satellites could carry ECM payloads to protect their own links or jam the guidance of inbound assets, functions that are technically feasible but raise the same escalation risks as firing back in any domain. If you jam an attacker's guidance from orbit, you've likely crossed a threshold that invites retaliation. A practical and less provocative form of active defense is active debris removal as a defensive policy. Removing large, high-risk debris fragments reduces collision risk and is a public good defense for the whole orbital environment. Programs that capture or deorbit dangerous objects are both safety initiatives and a subtle form of defense against the cascade effects that an adversary might try to create. In short, active defense is already partially feasible. Robotic servicers, software-defined radios, anti-jam systems, and improved SSA exist today, but moving from prototypes to operational defensive forces is a different matter. Each active measure carries legal, safety, and escalation hazards. Grappling or intercepting another nation's satellite can look, to that nation, like an act of war. So while MEV and RSGS-type capabilities, SBI concepts, and on-orbit ECM are technically within reach, deploying them at scale would demand new rules of engagement, robust attribution, and careful international diplomacy. Defending satellites is therefore an exercise in balance. Harden when you must, diversify and duplicate where you can, hide and adapt when under attack, and invest in SSA to see threats early. Pair that with a cautious approach to active defenses, because the tools that can protect can also provoke. In the end, technical capability alone will not keep space safe. Policy, norms, and multilateral cooperation must grow alongside engineering if we want resilient, usable orbits for the future. Let's shift gears and look ahead, not at the satellites of today, but at the battlefields of tomorrow. Because the future of satellite warfare won't be about lone, vulnerable spacecraft. It's going to be about swarms, constellations, AI-driven defense, and maybe even robotic space drones patrolling the orbital highways. First, swarms. The trend is already clear. Distributed architectures are taking over. CubeSats, smallsats, and mega-constellations are moving into low Earth orbit, or LEO, by the thousands. These constellations bring resilience through redundancy. With intersatellite links, dynamic routing, and hundreds of nodes, you can lose a few satellites without losing the network. Instead of total blackout, you just get graceful degradation, like a rainstorm breaking up a signal, but not shutting it down completely. The catch? Orbital congestion. Space situational awareness, or SSA, becomes harder. Collision management grows more complex. And the nightmare of a cascading debris event, the Kessler syndrome, looms larger with every new launch. Mega-constellations like Starlink, OneWeb, or Amazon's Kuiper show both sides of the coin. On the plus side, they're harder to take down in one strike. No single missile or a sat can wipe out thousands of nodes across LEO. On the downside, they offer more targets. A determined adversary might not aim to destroy them all, just to disrupt them selectively with uplink or downlink jamming, GNSS spoofing, or cyber attacks on ground networks. And there's geopolitics. In Ukraine, Starlink became a strategic military asset. Suddenly, a private company was a frontline actor in global conflict. That blurs the line between commercial infrastructure and geostrategic weapon. Now layer in artificial intelligence. Future satellites won't just be automated, they'll be autonomous. On defense, AI-driven payloads could handle onboard anomaly detection, autonomous collision avoidance, fusion of SSA data, and adaptive waveform management to dodge jamming and spoofing in real time. On offense, the same tech could be used to analyze signals, time a coordinated jamming strike, or reconfigure payloads on the fly. DARPA has already tested prototypes of this kind of autonomous decision loop. We are at the dawn of a machine-speed space battlefield. Then there are the so-called space drones. Robotic servicing satellites, think Northrop Grumman's MEV or DARPA's RSGS, already exist for refueling, repositioning, and repairing. But the same robotic arms that can save a satellite can just as easily grapple, block, or shove an adversary's asset. Norms like CONFIRS are trying to regulate proximity operations, but the technology is inherently dual-use. If conflict escalates, these servicers could quietly transform into orbital warriors. What about more dramatic weapons? Hypersonics and space-based strike systems have long haunted defense planners. The concept of kinetic bombardment, rods from God, is technically possible but politically explosive. Space-based interceptors, or SBIs, are feasible but costly and destabilizing. Hypersonic boost glide vehicles are more realistic in the near term, launched from Earth, skimming through the upper atmosphere, but stationing offensive weapons permanently in orbit would cross a major red line. It would be the full militarization of space. So what's the timeline? Near future, 1 to 5 years. Expect more test and demo programs, RSGS, MEV-style servicing, AI-driven SSA tools, and yes, more incidents of jamming, spoofing, and cyber interference. Space forces will expand, SSA networks will get denser, and commercial constellations will keep playing roles in real-world conflicts. Midterm, 5 to 10 years, we could see widespread deployment of autonomous defensive measures, onboard AI that reacts faster than ground controllers ever could. Small-scale active defenders or interceptors might appear as demonstrators. Political debates over rules, treaties, and orbital conduct will intensify. distant future, beyond 10 years, directed energy weapons like high-power lasers or HPM systems could migrate into operational space platforms. Entire defensive or offensive stations might emerge in GEO or cislunar space. Whether they do depends less on physics than on politics, arms control regimes, and budgets. Which brings us to the strategic and political dimension. Dedicated space commands are already here. The US created the US Space Force in 2019. China fields the Strategic Support Force integrating space, cyber, and electronic warfare. Russia's aerospace forces handle orbital assets alongside air and missile defense. And more nations are building specialized organizations to secure their satellites. Is a space arms race realistic? Absolutely. The US, China, and Russia are the frontrunners. But private companies are now part of the equation. SpaceX, Amazon, OneWeb, their constellations aren't just communication platforms, they're strategic infrastructure. When private firms become geopolitical actors, the arms race gets even more complicated. Could treaties stop it? The Outer Space Treaty of 1967 banned nuclear weapons in orbit, but it left huge gaps. Non-kinetic weapons, ASATs, cyber attacks all sit in a legal gray zone. The Paros Initiative at the UN, Prevention of an Arms Race in Outer Space, has tried to update the rules, but without binding controls, enforcement is weak. The likely outcome isn't a sweeping treaty, but a patchwork of confidence-building measures, soft law, and voluntary norms. In other words, not a new Geneva Convention for orbit, but a shaky code of conduct. Without stronger agreements, the future of space may look more like the Wild West than a well-policed highway. So, the future of satellite warfare is hybrid, resilient megaconstellations, AI-driven autonomy, robotic servicers with dual-use potential, and a political landscape struggling to catch up. It's part engineering, part strategy, part diplomacy. And the stakes couldn't be higher. Whoever controls space infrastructure doesn't just control satellites. They control the flow of information, the eyes and ears of modern militaries, and, in many ways, the backbone of global society. The question isn't whether satellite warfare is coming. It's already here. The question is how far humanity will take it.